Hi class. So we're starting the next video. So we're on the Gram-Schmidt process. Basically what we're going to do for this section is we are going to go through the Gram-Schmidt process and all the things related, orthogonal sets, things like that, projection theorem, with the general inner product. Okay, so before we talked about these things with the dot product or the Euclidean inner product, we're going to do this in general for all forms of inner products. Okay, so we're really just going to generalize that chapter, I believe it was 8.1 and 8.2 section that we covered previously. All right, so let's go through some definitions. If we have a set of vectors, v1 through vk, so k vectors, that exist in an inner product space. So remember, an inner product space is a vector space with an inner product defined on it. Then we say that this set of vectors is an orthogonal set if the inner product between any two of them are 0. Not to say that the inner product between a vector and itself is 0, right? Because that would mean that it's a 0 vector. But if the inner product between a vector and any other vector is 0, for all of these vectors, it will be an orthogonal set. Okay, so let's do a quick example. So let's consider the weighted inner product, U transverse times a diagonal matrix times a vector v. So if you remember the definition of a dot product, the Euclidean inner product was U transpose times v. Okay, in that case, we actually did have a weighted inner product, but the weights were distributed equally. It was 1, 1, 1. This D matrix was really just the I matrix, right? The identity matrix. And since the identity matrix does not distribute weights across anything in any sort of form, right, you don't even have to write the I because it doesn't matter. So remember, our definition for the dot product was U transpose V. So if we have a weighted inner product, we will have a diagonal matrix with different values along the diagonal because those will be the weights associated to each piece of the dot product that we're forming, right? So this is really just a weighted dot product. That's how you should think of the weighted inner product, okay? So this is our diagonal matrix, 3, 1, 2. So if I take a set of vectors, let's call them U and V, and I form this weighted dot product with U and V according to these weights, basically all I'm going to do is I'm going to do my standard dot product, 1 times 2 plus 0 times 1 plus negative 1 times 3. So if you notice the regular dot product here, I'll get a 2, a 0, minus 3. I would get a negative 1 from that, okay? But I'm not doing the standard dot product. I'm doing a weighted inner product. So I'm weighting each thing accordingly, okay? So my inner product, UV, is going to be just like my dot product, but a weight of 3 for the first terms, a weight of 1, and a weight of 2. So now when I do this, okay, I'm going to have 3 times 1 times 2, okay, 1 times 0 times 1, and 2 times 3 times negative 1 times 3. So now I'm going to get out a 6, a 0, and a negative 6, and I'm going to get out 0. So the standard Euclidean inner product, the dot product here, would not give me an orthogonal set. But the weighted inner product, according to these weights, does give me out an orthogonal set. So in this inner product space, these vectors are orthogonal. In the standard vector space, right, the standard dot product inner product space, these are not orthogonal, okay? But my inner product space now is according to this inner product, and they are orthogonal here, okay? So U and V are orthogonal in this inner product space. So let's go over another theorem. Let V be a set of vectors, and let this set of vectors be an orthogonal set. So each one of these vectors are orthogonal with all of the other ones, okay? And they are non-zero. So let this set of vectors exist in an inner product space. If that's true, then V is linearly independent. Okay, so these vectors, if each of these vectors are orthogonal to each other according to the defined inner product in my inner product space, then these are all linearly independent vectors. Okay, so let's do an example of that. So let's consider what is called an important class of polynomials. They're called the Legendre Polynomials. If you are in my DiffEq class, we kind of skipped this section last week, but we did have, there is a part in the book where we talk about the Legendre Polynomial, so we're actually going to talk about it now for us in linear algebra. We're not going to derive where these things come from, which is what we did in the DiffEq class, but in the in this class we're just going to use them to talk about to verify that they're an orthogonal set. Okay, so there's an infinite set of these polynomials. Okay, the way that they are formed is that you kind of they're built one at a time in increasing power. Okay, so what we're going to do is we're going to just take the first 4 of these things, right? We're going to show that the first 4 of these Legendre polynomials form an orthogonal basis for P3. So remember what P3 is. P3 is the set of polynomials that are of degree 3 or lower, right? So you have constants, first degree terms, second degree terms, third degree terms. There are 4 things here, okay? So the things here, to build a basis for this, there has to be 4 elements. So we're going to take the first 4 elements of the first 4 Legendre polynomials to form this. Okay, so the inner product that we are going to define for this, for the Legendre polynomials, the space that they live in, is the inner product between P and Q, is defined as the integral from -1 to 1 of your 2 functions inside this inner product being multiplied times each other. Okay, so the first 4 Legendre polynomials are 1, x, okay, which should make sense. Then the next one is a little bit different, okay, it's 3/2 x squared minus 1/2, okay, but when they're formed, they generally will look like this, with a constant in front. And then the last one of our 4, 1, 2, 3, and 4, is 1/2 times 5x cubed minus 3x. Now there's a way that we can expedite this and we can show that this is true, but we're going to go through all of the work by hand. Okay, so what we need to do is we need to show that these set of vectors form an orthogonal set. Okay, if we can show that these form an orthogonal set, then from the previous theorem we can say that they are linearly independent. And if they are linearly independent set of vectors, then they span a space, right? They generate a space, and that space that they would generate in this case would be P3. So they would form an orthogonal basis because they are orthogonal, and there's 4 of them in a space of dimension 4. Okay, so that's what we're trying to do here. So let's take the first set. We're going to take P0 and inner product it with P1. Now what we're going to do is we are going to basically take P0 with P1, P0 with P2, P0 with P3. And then we're going to do P1 with the rest, P1, P2, P1, P3. And then the only ones that are going to be left is P2, P3. So we're going to do this in a way that we can kind of just eliminate all the possibilities in a sort of intentional way, so that we're not like, oh, well, let's do these 2 and then these 2 and then these 2 and these 2 until we run out. We'll just kind of go through the list with each one. Okay, so the inner product for P0, P1 is going to be the integral from -1 to 1 of 1 times x, which is just integral of x. So as you can tell, this is an odd function, right, from a symmetric bounds. So it'll go to 0. We could say that, but if we did say that, we'd have to show that it is an odd function. But it's easy to actually just do the integral here. So we're going to do 1/2 x squared, evaluated from 1 to -1. which is just going to be 0, right? You're going to get basically 1/2 minus 1/2, and that'll be nothing. So for the next one, we have P0, P2. So that's the integral of 1, that's my P0, times P2, 1/2 3x squared minus 1 dx. And this will give us two terms to evaluate at the same bound. Okay, so up in the power, it comes down and it cancels with the 3. So I have a 1/2 x cubed minus 1/2 x squared. Evaluate it from 1 to -1. And I actually get these first two from the positive 1, right? 1 minus 1/2. And then I'm going to subtract, and then me plugging in -1 will give me these values. So I have two positives, two negatives, they cancel out, and I'm 0. Okay. The next one is P0 with P3. Okay. So same thing, 1 times this term from -1 to 1, right? And so when I do this, I have 1/8 times 5, or 5/8, and -3/2. Evaluate that from -1 to 1. And the same thing. So the first two terms are a 5/8 and a -3/2 from the positive one, right? 5/8 minus 3/2. And then I'll have the negative, so I'm going to subtract that. But these are evens, so it'll be positive. So I'll have a minus 5/8 and a plus, because it's a minus 3/2. So those terms are positive. These terms are negative. They're opposite signs. I'm also going to get a 0. Okay. So now we're going to come into where we're not multiplying things by 1. So we'll multiply x and P2 and x and the P3 for the next one. Okay. So everything here, it's not 3x squared minus 1. It's 3x cubed minus x. Everything's bumped up by a power. Okay. The integral will give me these terms out, right? I go up by 4, put it on the bottom. It's an 8. Same thing here. This is it goes up to 2, goes on the bottom, times the 1/2. Evaluate that from 1 to -1. And again, you'll get the same things with alternating signs. So we have a 0 out. Okay. P1, P3 will be the same thing. Everything in P3 will be bumped up by a power of x. Okay. So when I do my integrals, again, this will turn to a 5 and come down. The 5 will cancel. This will turn to a 3 and come down. The 3 will cancel. So I'll have a bunch of 1/2s, right? Evaluated at 1 to -1. These are odds, so the signs on the -1 will cancel, or I'm sorry, will be negative. So these signs will change and they'll be subtracted, so then they'll turn back into the same thing, right? Positive and negative on the last two. The first two are at 1, so that's positive and negative. Obviously, everything cancels here, and we get to 0. Okay. So on this last one, we're going to multiply P2 and P3 and integrate that from our bounds. Okay. So I will have this. Okay, and if you multiply it out and extend it out, you're going to have 1/4. You're going to have a 15x to the 5th. At the very end, you should have a plus 3x plus some stuff going on in the middle, right? So it should look like this. Now evaluate this from -1 to 1. I will have these three terms, right? These three terms of my polynomial, increasing their powers by 1, and then fixing the denominators. Okay. Obviously, I'm going quickly through this, so just make sure you're stopping and pausing so you can write this stuff out in your notes. Okay, apologies, you guys. But I'm going to evaluate this from 1 to -1. So for the positive, it'll be 5/8 minus 7/8 plus 3/8. For the -1, it'll be the same thing. I will subtract the exact same values because everything is a positive power. So I have this thing minus itself again. Okay, so everything will cancel and I will get a 0 out, right? So that was the last inner product I had to form. Okay, I got a 0 for all of these. Okay, so that means that all of these things form an orthogonal set. I had to inner product everything with everything else. Okay, and since they form an orthogonal set, from the theorem we had before, that means that they are linearly independent. And since they are linearly independent, and there are 4 of them, and they are, that means they span a space that has a dimension of 4, right? P3 has dimension of 4. There's 4 things in a dimension of a space of 4. So it's an orthogonal basis because they are orthogonal and linearly independent, and there are just as many of these basis vectors as they are for the dimension of the space. Okay, and that's how we show something like that, right? So let's jump to our next theorem. Okay, our next theorem says let V again be a set of vectors that form an orthogonal basis for an inner product space V. Okay, then for any vector in my inner product space, I can write it as a linear combination of these vectors. Okay, where these constant terms, not C1, C2, C3, in this case we're calling them S1, S2, S whatnot, right? Each of these SIs is really just the projection that we have, right? So the inner product of that vector that I have with one of those basis vectors over the length in that inner product space of that vector. Okay, so remember now we're computing length depending on how I'm defining that inner product. Okay, so I can call it in this form, and remember this inner product is now defined as whatever the inner product is defined as in that inner product space. Okay, so I gave you guys this formula last time we went over dot product, but I didn't give you an example. I gave you an example of 2 other things, the Gram-Schmidt and the projection onto a subspace, but I did not show this one. So for this section, I'm going to do the opposite. I'm going to give you an example of this, but I'm not going to give you an example of the projection to a subspace or the Gram-Schmidt, because you've seen that for dot product, so you know how it works. The difference is how we're defining the inner product. Last time I did not give you an example of this, so I'll give you an example of this, and then we'll just go through the formula and the definitions for projection onto a subspace and the Gram-Schmidt, which is exactly identical to what we had before. The only difference, again, is that it's not dot product, but some inner product that we define on this inner product space. Okay. So again, here, remember, I'm taking this vector, and I'm doing this to each vector in this orthogonal basis, right? So up to K. So let's do an example. Let's consider the inner product space of continuous functions from negative pi to pi. Okay. So that's my inner product space of continuous functions on this interval with respect to the inner product, not space, just to the inner product, defined as inner product f of x to g of x between 2 functions as 1 over pi from negative pi to pi of f of x, g of x. Okay, so that's how we're going to define my inner product here. Let V be the basis or the set of vectors, 1 cosine of x, sine of x. This is an orthogonal basis for V. If you don't believe me, you can verify this through the exact example that we just did previously. Okay, so you just have to take it at my word that these form an orthogonal basis on this space. This is actually sort of like a small introduction to Fourier series, Fourier transforms, for those of you who are knowledgeable about that in any kind of way. This is actually kind of a big deal. You cover that kind of stuff in a PDE class, but regardless, let's go through this example. Okay, so what we're going to do here is we're going to take a vector. In this case, a vector in this inner product space is a function, right? So let's take a function, and what we're going to do is we're going to write it as a linear combination of these basis vectors. So our vector function in this case, right, is going to be e to the x. Right? So that's going to be the vector that I'm considering over this interval. Again, I'm calling it a vector because I'm in a vector space. My vector space is a space of functions. Okay, and this vector has an inner product defined on it as such, so that's actually an inner product space, right? So the things that I'm working with here are functions because of the space that I'm in, right? So I'm going to write e to the x as a linear combination of these basis vectors as defined by in respects to this inner product. Okay, so again, what I'm going to do is I'm going to follow this formula. I'm going to break v down to some constant times a basis vector, okay, or function in this case, and each of those constants will be defined by the inner product form. Okay, so let's get started. I need to write e to the x in this form, okay, and really I'm just looking for these SI terms. That's what I have to find, okay. So if I write it in the notation, it's going to be the inner product with v1 with my vector that I'm looking at over the length of my vector in respect to this inner product times that vector, and I'm going to do that for the next three as well. Okay, inner product my function with the basis function over the length of that function in that inner product space. Okay, multiplied times that function, right? So it's going to look like this. It's 1 over pi from negative pi to pi of these two functions. So the first one is going to be 1 and e to the x. So that's just e to the x over the length of 1. Okay. The next one is going to be the same thing. The integral of, so remember on the bottom it's v2 dot product, or sorry, inner product v2. So that'll be cosine cosine. On top ex cosine times my cosine. And then for the next one, it's e to the x sine, sine and sine times my sine, right? So this is going to give me a constant out because it's a bounded integral, right, over another bounded integral. So this will be a constant times my basis vector, a constant times my basis vector, and a constant times my basis vector, okay? So I did all these in the calculator instead of going through them by hand. But again, if you were going to do this by hand, you are going to do it by integration by parts, okay? And so again, I'm not trying to spend a lot of time on this, right? You guys know how to integrate. So if you are to do this by hand, it would be integration by parts, evaluated at bounds, okay? And so you'll get some complicated form of e to the x for all of these things, which really simplifies down to sinh, okay? So this is 2 pi over sinh pi over 2, negative 1 over pi sinh of pi over 1 times cosine. And the same thing here with the positive sinh. So when I simplify this down, it will turn to 1 over pi sinh pi times 1 minus 1 over pi sinh pi cosine of x plus 1 over pi sinh pi sine x. And I do not want to simplify this. I'm not going to pull out that common term of sinh pi over pi, because the goal was to write it as a linear combination of these vectors. So I don't want to pull it out and then have it times 1 minus cosine plus sine. That's not the goal. I want to keep it as a linear combination because that's what was asked of me, right? So again, if you're not familiar with sinh, if you did decide to go ahead and do this by hand and you're like, I'm not getting out sinh, remember what sinh is. Sinh is e to the x plus e to the negative x over 2, I believe. I don't remember. It's one of them is plus and one of them is minus. Cosh is plus, sinh is minus, or maybe the opposite. I don't remember, right? But they both have the same form. 1/2 times e to the x plus e to the negative x, okay? So, and then one is plus, one is minus. I don't remember. But that's what sinh and cosh is, okay? So that should make sense because you're going to have e to the x here. And you're just going to get a bunch of forms of that when you do your integration by parts, okay? So that is how we do this. So again, apologies. I know I'd like to generally do all of this by hand and I show you how all of this works, but I know you guys know how to use your calculators for things like this, and you are also should be fairly decent on integration by parts. I prefer to do a table method. I don't know if I've shown that in this class. I know I do my DiffEq class quite often, but I would just, review that because you are going to be multiplying functions here and taking integrals for quite a few inner products. So if your calculator doesn't do it, just brush up on how to do those things by hand. Okay. So let's go to a definition. Okay. So let S be a subspace of an inner product space V. Okay, we can write that as S proper subspace V. So S can be smaller in size than V, or it can be equal to V itself. Okay, I think I've introduced this notation a little bit here, but this is the mathematical notation for a subspace. Okay, very similar to less than or equal to, right? If this equal sign is not there, then that means S is strictly smaller than in size to V. Okay, so in this case, we can think of S being the same size as V, but generally it's not. So let's say that S has an orthogonal basis made up of k vectors, okay, all orthogonal to each other. Then the projection of V onto S, okay, is given by this form. Okay, so very, very similar to what we had before, where we tried to write V as a linear combination of basis vectors. The difference here is that we're going to add all of those parts together to project V onto this subspace. Okay, so remember, these vectors have to be orthogonal. That was a problem that quite a few of you guys were running into as you were going through that 8.1 section. You're having a problem getting a correct answer for the projection. The basis has to be orthogonal. If it's not orthogonal, then you need to orthogonalize it with the Gram-Schmidt. You have to orthogonalize it, okay? So that brings us to the next theorem, okay, which is again a repeat of what we saw in the dot product section, which is let S be a finite dimensional subspace. So non-zero, there's something there in that subspace. And V is an inner product space. Then for any V that we have inside of this vector, the projection of V onto that subspace is going to be in that subspace. Okay. V minus the projection is going to be in the orthogonal complement. Okay, because remember, this is orthogonal to this vector, right? That's the component that's from the projection theorem, right? If V is in S, then V is equal to its projection, right? The projection of V onto S is going to be independent of the choice of orthogonal basis for S. So if I'm projecting V onto S, it doesn't matter what basis I choose, as long as it's orthogonal for S, this projection will always look the same. Okay. So now let's get into your guys' favorite, the Gram-Schmidt process. Again, it's identical to what we had for dot product. It is just the way we're defining the dot product is different because it's not a dot product, it's an inner product now. Okay. So let S be a subspace of an inner product space V. So S is a subspace of an inner product space with a basis S1, S2, Sk. Okay, it is not saying that this is an orthogonal set, it's just a basis. This space has a basis, and remember, the Gram-Schmidt is a tool for us to build an orthogonal basis so that we can do things like project a vector onto that subspace. Okay, so let's define V1, V2, and Vk in order by V1 being S1, V2 being S2 minus the projection of S2 onto V1. V3 is S3 minus the projection of S3 onto each of the previous vectors that we built already, okay, and so forth, okay, until the end, right? So I know this projection form is a little bit funky sometimes because this is a whole formula in itself. So since I'm such a nice guy, here it is in a formulaic manner. Okay, so it's the dot product, the inner product of v1 with that vector you have over the norm squared of the vector you're projecting onto times your vector you're projecting onto, right? So that's how this formula follows formulaically for all of these Gram-Schmidt process. Okay. Thanks, guys.